I'm very pleased to be lecturing here. This is the last week of the school, and judging by the quantity of listeners, the school was a success. I'm glad about that. And the iterated modular symbols, which I will be explaining, is a pretty recent piece of work, but my experience has shown that it's somewhat difficult to understand what it is all about unless one has some understanding of classical modular symbols. And classical modular symbol, sorry? Is that better? Okay. And classical modular symbols were invented about 40 years ago to throw some light upon even more, upon even older questions about number theory, L functions, and things like that. So after some thought, I decided that I will start with a much more classical introduction dedicated to some general facts and examples about arithmetical functions, Dirichlet series, modular forms, and tomorrow and the day after tomorrow I will be speaking about more recent things. Okay, so first of all, arithmetic functions and Dirichlet series. And for me, an arithmetic function will be just some sequence starting with term number 0 or 1. Like, for example, say the number of divisors of n, or the sum of some powers of divisor of n. So it will be denoted, say, sigma k of n. Or else just 1 if n is a prime, or say power of prime, and 0 otherwise. Or else say the case that I will be considering in a little bit more detail later on. You have some kind of power series, and an are coefficients of this power series, like this will define a Fourier series whose coefficients are explicitly given. In a sense, you can read this infinite product as a program for computations of an, and we want to understand these things. And sometimes these functions have nice properties, like when n and m are coprime, then so all the things, I don't want to say that all these properties, all these series are just the same. Sorry about the notation. Probably I should put something like that, not to confuse you. Then it is a multiplicative function, things like that. So in number theory, in classical number theory, there is a lot of such functions, and questions about them. Like, for example, what is the asymptotics of partial sums of coefficients when we take very many coefficients, like, or the case where an is a prime or a power of prime, then we are asking essentially how many powers of prime are less than n. And this is, of course, a very classical question since Euclid's time, and later on the primes pop up in the between integers in very regular way, so we at least want to ask whether there is some regularity in the average. Or else, are there some other formulas for ANs other than those that are used to define for ANs, than are used to define our AN? For example, in this particular case, this is the definition, and it turns out that coefficients of this power series do satisfy the multiplicativity property, but one doesn't see it at all from the definition. So there must be something else which shows you this particular property. What is this? How can one guess things like that? And of course, the classical approach to this kind of problems is to introduce a generating series, and as often as not, it will be a Dirichlet series. So whenever you have such a sequence, you are considering instead an analytic function, at least a formal Dirichlet series at first. It usually converges when the real part of S is sufficiently large, if AN is not growing too fast. And for example, this property is equivalent to the formal Euler product. This is the same as to say that we have such a product where this series is defined in this way. The transition from one side to another side is the classical Euclid theorem about existence and uniqueness decomposition of any n into products of primes. And whenever we want to answer a question of this type or of this type, this is usually translates into some problem about analytic properties. For example, if you want to count the number of primes or powers of primes not exceeding a given bound, then the classical strategy is this. You consider the Riemann zeta, which is just such a sum. You express it as Euler product, since identity is obviously multiplicative function. And you pass, for example, to logarithmic derivative, which makes from this product makes a sum. And this is already something which is close, its coefficient is something which is close to what we actually want to sum. So analytic properties of zeta and analytic properties of the logarithmic derivative, if we can make everything not formally, but in fact in the theory functions of complex variable, they sort of translate into something that allows us to produce a proof of analytic of the asymptotic law of distribution of primes. But then the questions that we had about individual coefficients translate into questions about analytic behavior of zeta of S. And we, of course, know that the key fact is that near S equal to 1, there is a pole of the first order. There is some analytic continuation to the left. And then using contour integration and things like that, we can produce asymptotic law of primes. Okay, so now the question arises, how do we approach the problem of analytic properties of such Dirichlet series? We do it via Manin transform. Manin transform is something which relates, on the one hand, the Dirichlet series, with the other hand, the function of complex variables, which is given by essentially Taylor series, or rather Fourier series, with the same coefficients. Why exactly this transform is so essential for understanding of this? And this is an absolutely key, although elementary, fact. I think this is one of the great mysteries of number theory, and I will not be able at all to explain it, but it is a very great invention. So what do you do is, well, this is, of course, this correspondence that I have written here is again purely formal. I have a sequence of coefficients here and a sequence of coefficients here, but there is an integral formula and integral transform that relates left-hand side and right-hand side. So formal Manin transform is something like that. I'm taking this function. Again, I'm assuming that whatever I should do, write integrals and things like that, that they can be analytically done in this way. I multiply it by a complex power of z, but my z will be running over imaginary half plane. So to make sense out of complex power of a complex number, I must tell which branch I take. And I take the branch which here is e exponential of logarithm, and this is a positive real number, so it's clear what do I mean, multiplied by s. Okay, and then I integrate with the multiplicative invariant measure. So I start with this series. I do this kind of integration. Again, after some analytic fuss about which I should think in each case in a more specific way. After some analytic fuss, I can permute summation and integration. And then, of course, each integral like that, I can calculate by replacing z by it, And then essentially I will reduce everything to the integral of this kind. And this is more or less classical gamma function with a scaling factor. So after all, I will get this with an additional factor, which is this. So what is important is that the purely formal transform, which appeals only to the coefficients, now becomes an integral transformation. And also, what is important, that we have these extra terms. Extra term. It turns out, again, a mysterious thing, one of the most mysterious things in number theory and algebraic geometry I know. If you compare this product, this Euler product, and if you take a sophisticated viewpoint that primes are points of the arithmetical lines, Z, and then if you recall that there is one more point, it's at infinity, so that completions of Z with respect to P are p-adic numbers, and with respect to infinity, which is a considerably more ancient product, are real numbers. So you might just might ask yourself whether there exists something like Euler product including some quotient at infinity, some factor at infinity. And it turns out that many various intuitive reasonings tell you that this is actually a term corresponding, a term which should be interpreted as Euler factor at infinity, at arithmetical infinity. It was discovered before such words could be pronounced with any meaning behind them, and still we cannot input what I have said right now into a picture which would be sufficiently general and sufficiently convincing. Nevertheless, this remains a beautiful piece of intuition which certainly in a great sense is correct. So thanks to the existence of this Manin transform, we get a next formation, this remarkable gamma factor. Okay. But that's not all, of course. How this Manin transform was used in the classical theory in order to deal with the basic problem. And let me remind you that the basic problem is, how can we understand analytical properties of such formal Dirichlet series in order to translate these analytical properties into information about arithmetics, into arithmetics about of n. And the crucial remark here was this: that for many arithmetical sequences an, the series like that has an invariance property with respect to a transformation which is in many cases just simply z goes to -1 divided by z, or more generally, and this is almost the most general case that is interesting in this context, something like that. How does it happen? Again, at first some examples. Just one example. Okay, suppose I want to treat Riemannian zeta. Let me write, instead of zeta of s, zeta of 2s. This is this then. And the respective formal Manin transform is something like that. Okay, summation is from n1 to infinity, but of course I can do it from n minus infinity to infinity, delete 1, and divide by 2. This doesn't matter much. What is essential is that after such a stupid change of variable, I get a series which is approximately invariant, not quite, I will not write exact formula right now, but approximately invariant with respect to this transform. Because of the classical summation formula, a sum of a function over integer points of the lattice equals to the sum of its Fourier transform over integral points of the dual lattice. And that's approximately what happens. Now, if you have something like that, then you look at your Manin transform, written as integral transform, and look what happens with the integration axis when you do this transformation. Okay, it is a sum of integration from 0 to I, and then from I to I infinity. And when you make this change of variables, this becomes integral, essentially integral from I to infinity, whereas this becomes an integral from 0 to I. So if your integrand is absolutely invariant with respect to -1z, so what you get then, you get an identity which is trivial, but it is not absolutely invariant. In particular, even if function f were absolutely invariant, up there an additional term which is essentially z power s. And of course, z power s is not absolutely invariant. It goes to this thing. And you have also dt divided by t, which gives you an extra 1. So what you get after applying this trick to Riemannian zeta function, you get a functional equation which is connecting z of s and z of 1 minus s. Well, it is formal, but then you look at the integrals, you see that the integrals converge, so everything is okay from this viewpoint, and this converges for large real parts of s, and this converge for small real parts of s, and so you get a functional equation and analytic continuation. Integral gives you analytic continuation, and this remarkable property, behavior with respect to such a transformation, produces functional equation. And then, of course, you get access to the mysterious critical strip for zeta, which is what happens in between real part of s0 and real part of s1. It turns out that invisible before roots of zeta lie conjecturally here. This is famous conjecture, Manin conjecture, still unproved. And it turns out that, for example, the question about distribution of primes turns out to be equivalent to the question about distribution of zeros of Riemannian zeta, because zeros become poles of zeta prime of s divided by zeta of s. And these logarithmic derivatives are exactly what appear in that formula which shows you the transition from integers to powers of primes. So you get one more great mystery of number theory, which I love to represent in the following form. There exists one probably arguably central object of number theory. Prime numbers exists in three different avatars. Prime numbers, zeros of zeta, and there is one more about which I will have not much to say during this lecture, but you should always keep this in mind, namely Frobenius classes of conjugate elements of Frobenius in the absolute Galois group. And for me, this is just the same one and the same object, this, and this, but represented in different, well, for us humans, in different realms of number theory, represented by totally different objects, whereas, in fact, this is just one and the same thing. And this is more or less open to human mind since Euclid time. This is since Riemann time. And this is, well, morally since Galois, but actually considerably later. And the relationship between them we do understand, and we do understand that sort of understanding of each of them is the key to understanding of another avatar, but it's still mystery and extremely fascinating. I think that's one of the most fascinating things in the whole number theory. Okay. Now, I am already close. Well, this was all very much classical subject. And now I am closer to what I will be speaking about. And here, modular group and modular forms appear. In the approach that I have taken, probably, let me put it here. In the approach that I have taken, the reason this object appear in this situation are purely formals. Namely, I have been considering Fourier series of this kind, and I want them to be invariant or almost invariant with respect to the transformation which I have introduced just because I wanted to explain where do you get functional equations for real series from. So I want to consider, well, this property, of course, already puts some restrictions upon the series I will be considering. I must say precisely what kind of invariance I want. But for the time being, the gist of the matter is that there is one more obvious transformation f is obviously invariant with respect to transformation z goes to z plus 1, just because it is a Fourier series. And these two together generate, at least if I will be considering the group of transformations with real coefficients and determinant 1. In this group, they generate subgroup which just simply consists of such transformations with integral coefficients. So basically, those Fourier series that have a chance to be embedded into this kind of calculations and produce some information about their inverse Manin transforms should behave well with respect to such a group. And so what remains to do is to specify behaviors of what I called invariance or almost invariance of f of z with respect to PSL2z. Well, okay, I have allowed also not necessarily transformation z to minus 1 over z, but to minus 1 over n of z. Then subgroup of finite index appears. And then study Manin transforms of such functions. A priori, it is not clear at all that the supply of arithmetical functions we get in this way is really interesting. Okay, we had 2 or maybe 4 examples. So what? In these particular examples, we were able to treat them in this way. So what? But it is, again, one of the mysteries is that actually the supply of arithmetic functions and their Dirichlet series obtained in this way contains, or conjecturally contains, an incredible amount of interesting, arithmetically interesting cell functions. For example, if you take just all elliptic curves defined over Q, and then define their L functions by counting points over various reductions modulo various primes, and produce from each prime an Euler factor like that, in a slightly more sophisticated way, and then take a product, then all elliptic curves, arithmetics of all elliptic curves, is contained in the supply of functions which are obtained in this way. And this is, of course, essentially what allowed Wiles to prove Fermat theorem. So we get already quite an unexpected and very interesting class. And actually, if we generalize this somewhat, and if we replace say PSL2R by more general reductive algebraic groups and naive functional equation or this invariance reductive groups and discrete subgroups, say arithmetical discrete subgroups, and formulate in a nice way the invariance property, then conjecturally the relationship generalizing Manin transform in this way will give us a great understanding of connection between Frobenius conjugates in various Galois groups and zeros or whatever of various new functions, and this is essentially the content of general Langland's program. So the seemingly technical trick that I've been describing under the name of Manin transform, which then sort of imposed upon me the desire to consider modular forms or modular functions with respect to a group of this type, actually was a gift, God's gift, which does which has much more general form that we could have expected on these examples, and which produces much more interesting arithmetics. Okay, this was the classical introduction, and now I will explain. I will, of course, now narrow my viewpoint again, and now I will say a few words about modular functions. No, that I cannot do. Oh, yes, there is a code. Yes, thank you. There is a code. Okay. Now, classical modular symbols. So in the classical modular symbols, what you're doing is you're considering this group PSL2Z and subgroups of finite index G here. And the reason I have explained through motivation of Manin transform, then you are considering forms. It can be slightly more general than that. For example, I can add a denominator. Doesn't matter much. But what is important is to specify the type of invariance with respect to elements of this group. And the type of invariance will be this. I will take a formal tensor differential of some power k, and I just will ask it to be invariant with respect to elements of this group. So if I have an element in this group, and I am considering it as a map of upper half plane to here, then these tensor differential forms are, of course, these usual differentials contravariant with respect to, well, this is, of course, holomorphic automorphism of H of upper half plane. And these formal tensor forms are, of course, contravariant with respect to G. And I will simply ask their invariance with respect to K. If you have something like that, then f of z is called a modular form of weight. Now, here I have a problem. I could never remember how K is related to the actual weight of form. So if anybody is very sure about it, please tell me. K minus 2 or divided by 2 or something like that. I will just say K, okay. 2K. Well, it's always a problem. By the way, even this formula is not accepted in all sources. Sometimes it's multiplied by a power of determinant, which is inessential here if I'm sitting in SL2. But if I will be sitting in PGL2, then there are discrepancies between exactly. But I will take this as the simplest possible explanation. Okay. With respect to G. Okay. And then what I'm doing, basically Manin transform studies integrals of this form. Well, you cannot integrate this form because the weight is generally not 1. So you simply multiply it by dz. And then, because in the Manin transform up there, you have some power s, so you do something like that. I forget about dividing by I. It's clear how to normalize this thing. So you study integrals of this type for analytic functions in the upper half plane, which are satisfying an invariance property of this type. And the story of classical modular symbols in the 60s started with a simple idea that since we are anyway transforming f using fractional linear transformations, and since we have, of course, a formula of variable change for an integral, instead of applying a transformation to the integrand, you can apply it to the path of integration or to both. So when you apply G to this path of integration, what do you get? Okay, ends will be G of 0 and G of I infinity. And as often as not, they will be finite and always, of course, rational numbers. And what is this? Well, this upper half line has a meaning not so much in complex geometry of upper half line as in hyperbolic geometry of upper half line. There is a very well-known matrix of curvature -1 on upper half plane. And this is a geodesic connecting 0 and I infinity. And when I apply G, I will get a geodesic connecting G of 0 and G of infinity. And generally, these are two rational numbers. So why consider only integrals from 0 to I infinity? Let's consider integrals of this type. And what is remarkable is that systematically studying integrals over geodesic, which is not also very essential, of expressions of this type when f is a modular form, one could obtain information about even classical arithmetic functions and related quantities, which was not known to classical mathematics. And this is how the theory of modular symbols appeared. So essentially, a classical modular symbol is an extremely simple, at least for PSL2. Classical modular symbol is an extremely, in one of its avatars, let's put it this way, the set of it's a linear functional defined on some space of modular forms depending also on some additional variable, Manin variable, I will call it, or Manin argument. And, sorry. And that's it. Classical modular symbols are just linear functionals on spaces of modular forms depending on n's and Manin variable, and studied systematically. When you consider alpha equal to 0 and beta to I infinity, you get the classical Manin transform. Okay. And what I will be doing tomorrow and the day after tomorrow, instead of considering just simple integral, I will be considering iterated integral. Expressions like that will be input into the thing several times, and I will get iterated integrals. The passage from simple integrals to iterated integrals of this kind will also need motivation, and I'll give some motivation tomorrow. But what I want to do now in the remaining 10 minutes, without really explaining how it happens, I want to show you what kind of new information we get about arithmetics just simply by replacing Manin integration with this more general integration. So I will return to the very beginning of my lecture and produce several arithmetical identities that dropped out just from this simple idea. Consider integrals of more general type, which was motivated by more general invariance property that simply z goes to -1 over z. Okay. Of classical modular symbols. Just examples. They are a part of a much more systematic picture, but just to introduce you to what we can get in this way. Okay, let's start with that one formula. So example number 1. Classically, the coefficients of this series are called tau of n, and they are called Ramanujan numbers. And one of the properties that Ramanujan proved was exactly this. So the respective Dirichlet series has an Euler product, which is not obvious at all. Okay. So the formula that can be proved using classical modular symbols is just an identity. For every n, tau is equal to the sum of 11th powers of all divisors of n plus additional expression, which essentially is obtained as follows. This turns out to be a common trait of all interesting formulas for coefficients of modular forms. We will be considering all expressions of n satisfying certain inequalities. I will write them later on. Primes says that you should look later on to the precise definition of the summation domain. But essentially, you take a quadratic form of 4 variables of signature 2, 2, and representations of n by this form. And then what do you sum? You sum a funny expression. 691 divided by 18 and multiplied by this polynomial in terms of this solution, plus, again, 691 divided by what? By 6, multiplied by this polynomial. So in particular, a corollary, which was known, was also proved by Ramanujan, that, I'm sorry, I think there is a minus here, I'm not sure, excuse me, maybe minus. A corollary proved by Ramanujan is that this and this coincide modular 691. And 691 is something that can be more or less properly described in terms of the third avatar, that there's 691 has something to do with Galois representations, Langlands dual to whatever. But this proof of Ramanujan's congruence via this identity was not known until the theory of classical modular symbols was developed. And I tell you that there is nothing really more serious than passing in this proof, than passing from this integration to this kind of integration. That's quite funny. Okay, one more application. When I was speaking about Dirichlet theories encoding interesting arithmetical functions, not only the functions themselves, but also, for example, values of this L series at integral points become an interesting matter of study. And I will say, yeah. Sorry? Here? This is something like that. 6. Oh, I didn't. Oh, I'm sorry. Yes, I'm sorry. How do I sum? Okay. The main domain is this. 2 deltas are positive. And then there are additional conditions. Either the same condition is true for delta primes, or large delta is a divisor of n, delta prime is n divided by delta, delta small prime is 0, and we have this inequality. So this is the summation domain. It's quite universal in many identities of this type. it appears as well. Okay. The second is this. It's now not for coefficients, but for values of Manin transform of phi at integral points, but not all integral points, but only which are in the critical strip. I will not define everything today, but only these values written as integrals. And they are essentially integrals of this kind. And critical strip is between 0 and 10. Not 1 as in the usual zeta function, but between 0 and 10. And it turns out that there are exactly two unknown transcendences like pi square or something much more mysterious that enter this story. But if you forget about this value which you don't know and just write the projective point corresponding to even periods, then you will get this story. And of course, 691 is the same as appeared before. For the same reason, it appears here as well. And a similar formula for odd, or values at odd points. And of course, you have functional equation which allows you to pass from one half of the critical strip to another half. So here you will have and there is one more identity which I will not write now because it will take some time, which is kind of down-to-earth corollary of Langlands type correspondence, what I liked to call a non-commutative reciprocity law, yeah?
That's 3 to the 4th times 3. In the denominator,
3 power 4 times, well, not 3, of course. What should it be? It should be 2 here. Sorry, thank you. And the last identity which I wanted to show, but just don't want to spend your time, it's a kind of non-commutative reciprocity law which is an identity containing at the left-hand side number of solutions, number of points of a very fixed elliptic curve, modular variable prime p. And at the right-hand side, it contains a similar sum over solutions when you put p instead of n. But here, instead of a polynomial in solutions, you have something which depends on behavior of all these deltas modulo 11. And 11, mysteriously, is the conductor of that elliptic curve whose points you count at the left-hand side. So the identity tells you that you have a pair, p and 11, and you produce something out of 11, and this is your elliptic curve, and count the number of points modulo p. Or else you produce something from p, which is this kind of Diophantine equation, and then you reduce solutions modulo 11, and you get the same result. I loved this formula when I first got it and called it non-commutative reciprocity law, and of course it is a part of more general picture, but later on it became clear that this is a very down-to-earth part of the general length reciprocity that in these particular cases can be sort of disposed of by elementary means. But in the whole length problem, of course, one doesn't really see something very concrete number theoretical formulas. And this kind of formulas you get is a very beautiful illustrations of the down-to-earth content of what you are doing. So again, my logic was, I want to do some number theory. I am considering Dirichlet series and Manin transforms. I decide that, well, I, meaning we, mathematical community, decide that the right-hand side of Manin transform is probably more important than the left-hand side and consists of modular functions. We look at the integrals and study a little bit more general class of integrals. And we get modular symbols, and we return and prove some beautiful formulas about the initial problems we have been studying. So tomorrow I will start explaining to what degree this can be generalized to the iterated integration.